In this video, we're going to look at some more practice problems dealing with the derivative function. So first, let's do another limit definition of the derivative problem, this time with a more complicated function, that is x to the negative 2. So before we even go any further, let's remember that this function, x to the negative 2, is the same as saying 1 over x squared. And it's going to be easier to think about that positive exponent instead of the negative exponent. All right, now let's get into the limit definition of the derivative. We have the derivative f prime of x is going to be equal to the limit as h approaches 0, f of x plus h minus f of x all over h. And for our function, we have that f of x plus h is going to be 1 over x plus h quantity squared. And when we subtract off the function itself, we have 1 over x squared all over h. Once again, if you try to plug in 0 for h at this point, you will get 0 over 0. That's going to happen every single time, and it means we have to do some kind of algebra to make this work. This time we're going to do a different kind of algebra. We need to first find a common denominator and make this into one big fraction instead of this kind of mess of fractions that we have at the moment. So we're going to find a common denominator here, and the common denominator is going to be x plus h squared and x squared. So we're going to take this 1 over x plus h squared, and we're going to multiply it by x squared over x squared. And then we're going to subtract off 1 over x squared, and we're going to multiply that by x plus h quantity squared over x plus h quantity squared all over h. And the reason we do this is so that we can create a common fraction in the numerator. We have now a common denominator of x plus h squared times x squared. And on the top, we have x squared minus x plus h quantity squared all over h. So now let's do some of the algebra we've been doing a lot of with these problems. We're going to simplify the top to be x squared minus parentheses x squared plus 2xh plus h squared all over x plus h squared x squared all over h. And we can see that we are going to cancel out an x squared in the top, and that's going to be the kind of needed thing we need to do, is to get rid of everything without h in it. We'll be left with the limit as h approaches 0. Note that we are going to distribute the negative to each term here. We're going to be left with negative 2xh minus h squared all over x plus h squared x squared all over h. And now I'm going to combine that into one fraction by multiplying by the reciprocal. Write this as negative 2xh minus h squared over x plus h squared, x squared, times 1 over h. And now we can cancel out an h out of every single term. We are almost done at this point. We have limit as h approaches 0 of negative 2x minus h over x plus h squared, x squared. Now, maybe you're thinking that we didn't do enough to cancel everything out, but it's okay to sometimes to just try plugging in 0 for h and see if everything works out now. In this case, it will. We have negative 2x minus, there's plugging in 0 for h. We have x plus 0 squared, x squared. And this is going to give us a negative 2x over x to the fourth. Note that we can cancel out an x here, and we'll be left with negative 2 over x cubed. And that is the correct answer for that. So this is a lot more algebra in this problem that we had to do. We had to deal with fractions in a couple different ways, but it still came down to canceling out an h in the numerator and the denominator. And after we were able to do that, we can just plug in 0 for h and we get an answer. In the next problem, let's look at a function and its derivative. So we're going to, first of all, sketch sine on the axis below. Then we're going to sketch the derivative of sine, just looking on the interval 0 to 2 pi. So first, let's do some labeling here to kind of see what we want to do. We're going to have 1 and negative 1, and we're going to have our special points pi over 2, pi, 3 pi over 2, and 2 pi. And sine is going to have the special points 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 0, 2 pi, or 2 pi 0. And then we connect them in a nice way. And there is our sine of x on the interval 0 to 2 pi. So now what we're going to do is we're going to sketch the derivative. So here is the function, and I want to sketch the derivative, f prime of x, on the same axes. So all these are going to be labeled the same. Here's pi over 2, pi, 3 pi over 2, and 2 pi. And let's start with the horizontal tangent lines. It looks like we have 2 points where we have a horizontal tangent line. That's the top of a mountain, bottom of a valley. And at those points, the derivative is going to be 0. That's at pi over 2 and 3 pi over 2. So here the derivative is equal to 0. That means we are on the x-axis. Then we're going to think about the derivative. We're going to go from positive to negative as we go from increasing to decreasing, back to positive. And what this is going to look like is something like this. We start positive, then we are negative, back to positive. And you may notice that this is a very special looking kind of function. In fact, this is cosine of x on 0 to 2 pi. And it is true that the derivative of sine is going to be cosine, and we'll show that in chapter 3. There may be some kind of more work we have to do to kind of think about how high the derivative is going to be. Does it actually go to 1 or does it go further than that? We can think about maybe picking a special point like at pi and looking at the tangent line here. And that tangent line, you think about its slope, you can kind of guess that maybe the slope is at most -1, or sorry, at least -1. You can kind of do that for all of these points, and you can verify that it will be exactly cosine on those points. What's the important thing to see here? Knowing when the derivative is 0 and knowing when the derivative is positive and when the derivative is negative. One last question. We're going to go backwards this time. Here is the graph of the derivative. So here is a graph of f prime of x. So we're going to use this graph to give us some information about the original function. This is backwards from what we did in the previous problem. So given the derivative, I want to find on what intervals is f of x increasing, decreasing, and where do I have a horizontal tangent line? Well, we know when f prime is greater than 0, then that means that f is increasing. So in the graph of the derivative, I'm not going to look for when the derivative is increasing, decreasing. I'm going to look for when is the derivative greater than 0. That is above the x-axis. And the interval there is going to be, I want to put, this is going off in both directions. So the interval is going to be -infinity to looking like -1, and then 1 to 3, and then 3 to infinity. No, we're not going to include 3 because 3 is a special point where the derivative is 0, but we have those 3 intervals. We're looking at x values here. So -infinity to -1, 1 to 3, 3 to infinity. What intervals is the function decreasing? That are going to be the points where the function is below the x-axis. And that's just on the interval -1 to 1. Quick note here, we're not going to use the union symbol to connect intervals for increasing and decreasing. We're going to use commas, not union symbol, for intervals of increasing, decreasing. And with how we introduce increase and decreasing, it doesn't really make much of a difference, but mathematically speaking, it doesn't actually work if we have the union symbol based on the definition of increasing and decreasing. Also, we're just going to be using parentheses. We're not going to use the closed brackets ever for those intervals. Last question, at what point is there a horizontal tangent line for f of x? And that are going to be the points where the derivative is equal to 0. That's where we have a horizontal tangent line. So that's going to be at x equals -1, 1, and 3. So just take some practice to get used to going back and forth. Here we're looking at above and below the x-axis to figure out increasing, decreasing, instead of finding the intervals where it's increasing, decreasing, going backwards from the function of the derivative.